All right, so in problem 8, it states that the overhead reach distances of adult females are normally distributed with a mean of 197.5 centimeters and a standard deviation of 8.9 centimeters. Part A states, find the probability that the individual distance, meaning one distance, is going to be greater than 210.90. And part B says, find the probability that the mean of 15 randomly selected distances is going to be bigger than 195.7. So there's going to be some differences to the way that we solve parts A and B. So for part A, first of all, since it says individual value, and I know that the distribution is normal, I can draw this bell-shaped curve. And I'm looking at this in terms of x. Okay, so x in this problem represents the overhead reach distance. Now, at the center of your distribution is the mean. So the mean is 197.5. You have the standard deviation is 8.9. And the value of x is 210.90. So 210 is somewhere here on our graph. And we have a right case. How do I know I have a right case? I have a right case because it says that it's bigger than 210.90. So I have to shade in this piece, basically the right tail. Okay, so how do I solve this using our graphing calculator? Well, if you think about it, our distribution technically starts at 210, and this goes all the way in this direction, all the way to the right. So when I do the normal CDF, I'm going to do normal CDF of 210.9, because looking at my drawing, that's my starting point. I'm going to end all the way at infinity, or I could just write these repeating nines. Then we go to the mean, 197.5, followed by standard deviation, which is 8.9. So if I enter this into the calculator, I should get my answer. So this would be second bars, normal CDF, 210.9, comma, repeating nines, 6, 7, 8, 197.5, comma, 8.9, close parentheses. So we would get 0.0661 if I round it to 4 decimals. And that would be the solution to part A. Let me know if you get that in your calculator.
Yeah, I got that.
Sweet. Okay, now we move on to part B. When I move on to part B, things are going to change just a little bit. Now we have to find the probability that the mean of 15 randomly selected. So that tells me a couple of things there. That tells me that my variable of interest is no longer x, but x bar. And it gives me the sample size. The sample size there is 15. And we have that the sample mean must be bigger than 195.7. Okay, so here's the bell-shaped curve again. We have x bar this time, sample means. So we know x bar was equal to, for this problem, it's going to be 195.7. We have the original mean, the mean of the population was 197.5, so that's in the middle. Standard deviation was 8.9, and n is equal to 15. So I just had to write those things out. So here's in the center, 197.5 somewhere around here, let's say, is going to be 195.7. So this point is 195.7. And we have a right case because it said greater than. So when I make my shadings, I shade to the right of this value, 195.7. And now I do the NormalCdf command. So just looking at our image, if this is my starting point, I'm ending all the way to infinity because I have a right case. So we do normal CDF of 195.7, comma, all of these repeating nines. So there should be about 8 of them. 8 of them will do. Followed by the population's mean, 197.5. Standard deviation has to be 8.9 divided by the square root of 15. So remember, we're no longer dealing with x, we're dealing with x bar. So the standard error was the correct terminology for this. The standard error is the standard deviation divided by square root of n. Now we do this in the calculator, we get second bars to get NormalCdf, and we enter our values. 195.7 is your lower bound. The upper bound is the repeating nines. Then the mean of the population, followed by the standard deviation divided by square root of 15. So you got to do 8.9 divided by second x squared to get the square root. 15, just move the arrow key, put close parentheses, hit enter. All right, if I round my answer to 4 decimal places, we get 0.7833. Let me know if you get this answer as well.
Yeah, I got it.
Okay. So again, the calculator is helpful with this because it tells you, like, okay, depending on your cases, you know how to enter your lower bound and upper bound values, right? If it's a left case, you know that we have to do the negative 9999 followed by x being the upper bound. But if I do a right case, then my lower bound is the value of x or x bar. Then you do the repeating nines, then the mean, followed by standard deviation or standard deviation divided by square root of n for the sample means. In problem number 9, we have one more problem related to this. And if you guess, well, we did the left case, we did the right case. There's only one more case to talk about, and that's the between case. To me, the between case is a little bit easier to deal with, only because it gives you precisely your lower and upper bounds, right? So let me read problem 9 and make a little bit sense of it. It states that assume that the amount of weight that male college students gain during their freshman year is normally distributed with a mean of 1.1 kilograms and a standard deviation of 4.5 kilograms. Part A states find the probability that one randomly selected, meaning individual value, male is between 0 to 3 kilograms. So again, we're going to deal with the between case. The 0 to 3 are important numbers now because there's now 2 values of x that I'm dealing with. X equals 0 is my lower bound. X equals 3 is my upper bound. Okay, so for part A, if I want to find the probability of one randomly selected male is between 0 to 3, I first make my normal distribution. So labeling in terms of x, drawing this bell-shaped curve. Not the best bell shape, but we'll work with it. At our center is the mean. So the mean is 1.1. Standard deviation of 4.5. And I have 2 x values. I have x1 or a for my lower bound. That's going to be equal to 0. Oops, sorry. I have x2 or my b value. That's my upper bound, which is 3. Right, so this is your lower. This is going to be my upper. And of course, when I make my shading, this is the between case. So 0 will be located somewhere here, let's say. Let's say somewhere here is 3. So I'm basically shading all of this good stuff. Basically almost the entire graph looks like it's getting shaded. So when I do the normal CDF command, it's going to be normal CDF of 0, 3, 1.1, 4.5. And when I compute this, we should get a value. Just move this away. Oops, sorry. Okay, so let me work this out in the calculator. You do second vars, normal CDF, 0, 3, 1.1, 4.5. And you hit enter, you get 0.2601. If you got something a little different, let me know.
You said if we got what?
If we got something a little different than my answer.
Oh, give me a second. Let me put it.
Sure.
I got the same.
Okay, cool. Let's try it again for part B. So in part A, again, I was dealing with just individual value, hence why I labeled this graph in terms of X. But when we solve this problem now for part B, it says find the probability that the mean of 35 randomly selected adult males is going to be between 0 to 3. So I'm dealing with, excuse me, sample means. So when I draw my bell-shaped curve, all right, this graph came out a little bit better. This will be in terms of X bar, sample mean. So at the middle is going to be 1.1. That was the mean of the population. We know standard deviation was still 4.5. We have a sample size of 35, which by the way is bigger than 30, so it makes it automatically normal. And just like the original data, it was still normal. So hence why we're dealing the normal distribution. And lastly, the values x1 or x bar 1 is going to equal to 0. X bar 2 is equal to 3. So I'm shading in this piece, and we're looking at it again from 0 to 3. Bang. So normal CDF, 0 to 3, lower to upper bound, followed by population mean, followed by the standard deviation, divided by the square root of n, which is 35. So second bars, normal CDF, 0, 3, 1.1, 4.5. No, sorry, 4.5 divided by square root of 35. Round your answer to 4 decimals, you get 0.919. Yep, 0.9197. 0.9197. And those are your solutions to problem 9.